Welcome back. Awesome, awesome. Welcome, welcome. I have a haircut now. Oh, okay. Okay. One is the title. Put that down. For a fact, we got that one done. We have rest. We have 101. Okay. Hello, hello. Awesome. We're going to be starting in 5 minutes. Great to see you guys. We're just going to wait 2 more minutes and then we'll get started. Okay, I am going to start us up. Once again, as always, thank you so much for coming by on the weekend. Week 4, I think I said this every single week since week 2, but this is when stuff really gets super interesting, in my opinion. We're working with a new model, a new technique. I think you're going to find it being a very interesting data set. I know for a fact you're going to learn a bunch. So this is part 1 of our 2-week little entree into something called convolutional neural networks, which are used a lot in image processing. We're going to talk about it a bunch. So yeah, let's go over what we're doing today. And this week is called Crazy Convolutions. Fitting. So the 2 things we're going to talk about: convolutional neural networks and something called batch normalization. This is not very representative of how much time we're spent. I think I have about 100 slides on convolutional neural networks, and I have 1 on batch normalization. So this is a heavy convolutional neural network based presentation today. So as always, we're going to start with the problem. This week's problem, I know I like to make it a little silly, make it a little fun. This one's a little more serious, but let's get into it. So the problem is classifying human faces has been a difficult to solve problem for machine learning engineers for decades. They've been working on this since the 80s. While humans find it easy to look at pictures of people and discern gender, ethnicity, and approximate age, computers can find it more difficult. With the recent advent of deeper neural networks, algorithms are getting better and better at learning how humans look. Our goal today will be to take a series of images and try our best to algorithmically predict age, ethnicity, and gender of photos of human beings. Okay. We're going to get a little bit more. This is where I want to take the opportunity, and we're going to talk about at the end a lot about deep learning ethics specifically, because you guys, I know we've just been playing around on Google Colab and playing around with PyTorch, but you guys are working with an extremely powerful way of coding. We're seeing more and more gains. It can do scarier and scarier things in the future. And we have to make sure that we're designing our algorithms to be fair to humanity and being used in a progressive way. Because with great power comes great responsibility. And it is the case when anything groundbreaking comes out in the world. And as deep learning develops, we're going to have to ask those questions. So we're going to talk about that a little bit at the end. So let's talk about the data set. Okay, so the data set, we have 23,705 images. Each image is 40 by 40 pixels. Last week, we worked with something called the MNIST data set, which was the handwritten digits, which was 28 by 28. So our images are getting a little bit bigger, a little bit more complex. but you still can see there is a lot of pixel degradation, and these images are a little bit blurry, and they're in black and white. But that should make it easy for us to train. Smaller images take less time to train on. Each image, once again, like I said, is grayscale, black and white. We are going to be splitting up our data set into training set of 19,000 images and a test set of 4,705 images. As a reminder of training and test set, we've talked about this in the past. Training set, we are using our training set to actually teach our model. It is the textbook. It is everything that we need to learn about the features of a human being and how that correlates with our labeled set. And our test set, we are going to use to make sure that our algorithm, instead of copying the textbook and remembering what pixel values coordinate to what label, we're actually going to make sure that if you give it a whole new batch of faces, it does a good job at predicting human beings. We want our model to be good at predicting age, ethnicity, and gender of anybody, not just of our training set. Okay, so all images have 3 labels associated with them. That is of age, which is a regressive number. We're going to get into that. Ethnicity, which is classification, and also gender classification. So we can see this little girl, bottom left, the label condoning to her, sorry, the 5 right here, that is a typo. I try to get rid of that, but I'm using an old slide, I guess. She is age 8. Her ethnicity is 0, which correlates to a white person, and her gender is number 1, which correlates to a female. We're going to get into how those labels work in the future. So how are images represented? A tensor, so 3-dimensional array with a shape of 1, 40, and 40. I hope you guys are getting used to working with these tensors because we use them a lot in PyTorch. So the first dimension, 1, you can read it as 1 color dimension, black and white, 40 pixels high, 40 pixels wide. We've been over this. White pixel values have a value of 256. Black has a value of 0. Gray pixels intermediate. Okay. Cool. Next one. So this is where we have all of our images, and this is how many labels are concerning to a certain age. So we have a lot of 1-year-old children. Over here, big spike of babies. We have a bunch of baby photos. We also have a bunch of 26-year-olds, 20-year-olds around there. We have not a lot of old people, I'm going to have to say. There are some data set reasons for that, and then there are some cultural reasons for that. First of all, this is an amalgamation of a bunch of different data sets. So I think this is put together. They have a data set of babies, just newborn baby faces. And also celebrities. There's a bunch of celebrities together in this data set, and then just random pictures put together. And they basically put those together, crunch into one data set so you can have more data to train on. So some of these spikes are from the data sets, and also a little bit more culturally. It tends, I think a lot of us here are around 20. We like to take photos of ourselves. So there's more photos of ourselves out there. It's kind of hard to get photos of 14-year-olds, all that angst. So that's it. We also have skew of ethnicity and gender. And this is one of the things we're going to talk about with ethics of computer science. These labels for ethnicity condone to 0 is a white person, 1 is a person of African descent, 2 of Asian descent, 3 of Indian descent, 4 is a Hispanic descent individual. We can see that this data is skewed, okay? And that is one of the big ethical problems coming here. We have to make sure our data is representation of people. We're gonna save that big topic to the end, once again. But right now we have enough of each different ethnicity group that we can train a model and it'll be too good. It's not too skewed. We have a distribution of gender, it's about 50-50 of men and women, which makes sense because there's about 50-50 distribution of men and women out there. Okay, so now we've gone over the data set. Let's get into convolutional neural networks. And this is a fun topic. I really like learning convolutional neural networks when I first learned them. So I hope you do too. Okay, so remember, I showed you guys a graph. Different neural networks for different purposes. Number 1, what we've gone over, we've done the classic neural network. Classic deep learning technique used in many applications. We're going to be continuing using this in the future, but we've delved into that. We're moving now into convolutional neural networks. So they are neural networks designed for visual imagery analysis, and we're going to do some analysis of human images. Okay, and then last week we were going to get into recurrent neural networks. Next week, we're also going to do convolution. Okay. Convolutional neural networks, often used with fully connected neural networks. They're used in conjunction. So you can see in this image, the convolutions are these boxes. We're going to get into what those boxes mean. Though that is your convolutional neural network, you'll create it. You'll create an output. You create massive cubes. What you do with those cubes, you can flatten them out and you can use those as inputs for a neural network in the future. That is what we're going to do. They're regularly used in classification problems. We're going to use it as a classification problem, but they're also used in regressive problems. Next week, we're going to get into a completely new type of topic called a bounding box issue or a bounding box problem. Works best with images. It has other applications. You can use them in something called natural language processing that you've been using in the past, but they really find their home in images. They were designed for images. They work best on images. And if you look at the corpus of deep learning papers, all the big journals, you'll see them absolutely everywhere when it comes to images. We can see that the CNN, so the convolutional neural network, being used to classify handwritten numbers. This number 2 should be quite familiar to you. We did something very similar last week, except we just put the pixel values directly into a fully connected neural network, or a linear neural network is also what it's called. They're the same thing. This time we're going to take another step, do some convolutional neural networks, and we should get better results. Yeah, awesome. So we are used to thinking a little bit like this. This is my example from 2 weeks ago. And you're putting in different factors into a neural network. How close is a city to the sea? What country does a city belong to? What year is it? So those are what we're inputting. That's what the data we're putting in. And we're trying to figure out that given all of these features, what is the population of the city? And what we figured out is that these nodes can build upon each other. They can ask questions and build upon these questions to create more complex analysis. So if we're passing in how close a city is to the sea, what country does the city belong to, and what year it is, this network right here could connote to does this country have an abundance of food? So for example, in places like China in the 12th century, they had a lot of food because they were a rice growing population, and rice is very high calorie. That's why they could sustain such a big population. So there was an abundance of food, but in 2021 in Canada, I can go to the grocery store. I have a lot of food, right? But there's different factors. We can also ask, would this city have railroads at this time? How does that affect populations? Okay, those are all layer 1 questions. We can build upon those questions in layer 2 by connecting those layer 1 questions together. So this neuron up here makes the conclusion that a country was able to move food on the railroad, because previous layers asked, is there abundance of food and were railroads available? So using logic, you can deduce this together and create a really apt representation of a real life question. Okay, so that is how neural networks work in theory. In practice, we find neurons just aren't deep enough to work that way. In fact, if you really do a full analysis of neural networks and you look at, for example, of the MNIST dataset, it looks kind of random. It just so happens that the parameters we do create good results, but there isn't a clear, succinct building up of questions. So we lose performance in that sense. We can struggle a little bit. So what we really want is a way to build these questions upon each other and create profound answers at the end by building on small questions. Okay, so that is what convolutional neural networks do. Each one of these layers in this cube right here is a question, and we're going to dive right into that. So let's go to an example, okay? How it does it in convolutional neural networks, if you've seen any pictures of convolutional neural networks before, they're big on something called filters. Filters drive convolution. Convolutional neural networks utilize filters to make statements about an image. And you're going to see how that works, and it's very simple once you get down to the nitty-gritty. Each filter asks a different question about the image. Filters get smarter the deeper they are in the network. So at the beginning, the first filters that go on that image could be asking, is there a horizontal line there? It'll look at the pixel data and deduce if there's a horizontal line. we're going to build upon that. And at the very end of the neural network, at the very end of the stack, it can be asking more complicated questions. Is this a 7? And of course, when we're trying to classify numbers, having a good, succinct answer to is this a 7 is a great way to classify a 7. Okay, so this is what a filter looks like. A filter is a box of certain pixel width. So in our example, in the future, we're going to be using a filter of 7. So it's 7 pixels wide and 7 pixels tall. And what happens is you place it on an image with a question. Okay, so it's going to be looking at the top left of this image and asking the question, is there a horizontal line here? Okay, so right now we're looking at the top left of the image, and we can very clearly see there's not. It's a black box. There's nothing there for us to look at. So we write down no. We move over again. Same. No horizontal line. We write down no. Right? We keep sliding it across. Again, no. Sliding across. No. Once again, no horizontal line here. But here's when it gets interesting. Here is where it gets interesting. We can see very clearly that there is a defined, clear horizontal line. So the filter, which asks the question, is there a horizontal line here, will give you an answer. And it'll say absolutely yes. And it'll store it at this position right here. We keep going. Yes, there is another horizontal line right here. It'll store in the position next to it. So we can kind of see that it is keeping the image shape, the horizontal lines being in around the middle of the image, cosine with, this is called a map. In the middle of the image, we can see that the horizontal lines are represented in the map. It'll continue. No, no, no. There's a line there. Is it horizontal? No. No, no, no. Same thing. No horizontal line. No, no. So we have a map right here condoning or talking about specifically horizontal lines. And it gives us information about the horizontal lines in the image. So what it'll do next is it'll ask another question. These convolutional neural networks can ask thousands of questions. The biggest ones, they'll ask thousands and thousands of questions. But this one is going to ask, is there a diagonal line from the bottom left to the top right? Nope, nope. We're going to skip. It goes, no, 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 no. And then it gets here. We can see there is a diagonal line. It's not the cleanest diagonal line ever. But we're going to say yes with a caveat, yes with a question mark. Next week, when we really dive into this, we're going to be talking about filters a lot more. And we'll actually see that these values are not discrete, they're regressive. So instead of being a hard no, it'll be like one of those percent values. So it'll say like if there's a 0.1% chance that there's a horizontal line here, or a 100% chance that there's a line here. So maybe this could be, there's a 70% chance that there's a line. We're going to continue. When it gets here, very clearly, yes, there is a diagonal line from the bottom left to the top right. Continue, continue, continue. Once again, horizontal line or diagonal line, we found it. Boom. So we have two maps from our two questions. We have one that says, is there a horizontal line here? And is there a diagonal line from the bottom left to the top right? Those are our two layer one questions. In this example, we're going to have two layer one questions, right? So let's get into layer two. How do we get into layer two? What we do is we stack the tables. So remember when I talked about those cubes and they have like they're 100 deep? What we're doing essentially by stacking the tables is we're making a cube that is 2 deep. So it is 4 by 4, and it has 2 values in each grid. Okay, so we take that cube and we have another question. We're going to be doing the exact same thing, but instead of sliding across those pixel values, we're going to be sliding across those questions. And with this question, we can ask a more high-level question, something more conducive to labeling an image as a number. Okay, so the question we're going to be asking now is there conclusive proof that this is a 7? Which is a brilliant question to ask. If you can get conclusive evidence that there is a 7 there, that's a great way, step towards classifying a number, right? So once again, filter. This one is a 2 by 2 filter. Before we were doing a 7 by 7. And it's going to do the exact same thing. It's going to slide around and make assertions. So let's see what is passed into this filter. Oops, let's go back. So the top layers up here, if we remember, those are our questions. Is there a horizontal line? So all of these, the no, 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 yes, yes, no, 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 no. On the top, those are all our horizontal line questions. And at the bottom, those are our diagonal line questions. Okay. So the filter is going to look at that. And if it's smart, if it's trained well, it's going to be able to create good predictions. So in this filter, all you're passing into it is that there's a horizontal line. Doesn't really mean there's a 7, is there? Could be any number. It could be a 5. 5s have horizontal lines in them. 2s have horizontal lines in them. There's a bunch of numbers with horizontal lines in them. So if we move over sliding, now this is a little bit interesting. We have proof that there's 2 horizontal lines next to each other. 7s tend to have long horizontal lines. So if you have 2 horizontal lines next to each other, that could be pretty conducive to a 7. On top of that, we have at the same pixel spot, there is a diagonal line probably. We have about 70% chance that there's a diagonal line. So if you're looking at it, this filter could say, yeah, we're getting there. That is not a bad set of evidence for a 7. We can continue it. Not really in this case. We have 1 horizontal line and kind of a diagonal. It's not good enough. Keep moving. We just have 1 horizontal line here on the top right. Now, whoa, mama. This is a lot of proof right here. We can see that there is 2 horizontal lines next to each other, which is this yes and this yes. And on top of that, we have a bunch of diagonals. There's probably a diagonal here, and there's definitely a diagonal underneath it. So we have 2 horizontal lines and 2 diagonal lines. That looks like a 7 to me. If I'm this filter, I'm putting an emphatic yes right here. There is conclusive proof that this is a 7. And we're going to continue this. We continue this, we continue this, we continue this until we get 9 values. What we're going to do with these 9 values is we want to come up with, just like what we did in the MNIST test, we want to come up with percent values that it is of that number. So we take this, we flatten it out. So all we do is we take those rows and we string them together. We can see that it's a no, yes, no, no, yes, yes with a question mark, no, yes with a question mark, no. If we string it out, it's the exact same time. No, yes with a question mark, no, no, yes, yes with a question mark, no, yes with a question mark, no. Exact same thing. And then we take those values and we pass it into a neural network. And with that neural network, we get our answers. Okay. I'm not going to go too into the neural network. We've been over it before. But this is a brilliant way of training a classification problem. Okay. So deeper convolutional neural networks will ask many, many questions. They'll be more complex. The brilliant thing about convolutional networks and neural networks in general is that we don't have to define the questions. The questions will be defined for us. The model will actually learn to ask the right questions. The linear component, which is the same thing as just a regular neural network, is a linear layer. Works the same as last week's, but now instead of having pixel values inputted, the model has answers to high-level questions as inputs. So if you're a neural network and you are going to be inputted 758 pixel values, that's not really conducive to a great set of information to transform into a label, right? It's kind of hard. The neural network has to do a lot of work. It can look at the different pixel values and create a neural network and come to a solution, actually come up with great success. We did it before. We had a 97% accuracy with just using the neural network. It can do it, but it's a little hard. It's a little strenuous. It's a lot easier for a neural network to be passed in values like this. For example, it's getting passed in this variable right here that says this is a 7. It says there's conclusive proof that this is a 7. We are so sure of it. And it's taking that as input. And it's very easy for it to draw that bridge to the conclusion that this is a 7. It's doing essentially no work. It makes it a lot easier for the net. Okay. This will allow linear models to come up with better conclusions. Okay. So let's go back to this. We can see in our model, often used with fully connected neural networks. Check. Used regularly in classification problems. You can see how that works. Big check. Works best with images. We can see why it works best with images. Those sliding filters are specifically great at picking up shapes. So we talked about horizontal lines. They're great at picking up textures. So we'll see in the future, we're going to put in pictures of faces. They're really good at picking up things like hair texture, because hair has a certain quality to it, a certain shape to it, and the model can discern this is hair. Same thing with if you have high enough pixel values. We won't be able to do with this because it's 40 by 40 pixels. The images are really small, but they can pick up on like skin texture, pore texture, different shapes of your nose, shapes of your lips. And it can take those little tiny shapes, those horizontal lines and vertical lines and little arrows and different texture qualities, and it'll build upon that and say, if you have two horizontal lines and then a curve, that could be conducive to being a lip. And lips are shaped in different ways for men versus women, for different ethnicity groups, for different ages. It can pick up on wrinkle textures, which is obviously conducive to an older person. Okay, awesome. So the big question, because we talk about it every single week, are where are the parameters? These parameters are sneaky. I'm not sure if you guys found them. If you're paying attention, you would find them, but I don't know if you did. Okay, awesome. So looking at this, where are the parameters? Where are the parameters? Is it our yes and no questions? Not really. Those are our inputs and our outputs. The parameters itself, and if you remember, I like to put my parameters in red. The parameters is the question itself, okay? The parameters of the convolutional networks are the filter questions. So what that means is there is a numerical representation for those tough questions. We train those numerical representations. We do not need to manually ask those questions. The models will learn what questions to ask. So isn't that great? As deep learning engineers, we don't have to do anything. The model will do it for us. We don't have to ask those tough questions. The models will learn what questions to ask. So you're basically doing nothing for your job, and you get Google will pay you $200,000 a year for it. So it's a good life. Not actually, a lot of work, but you see what I mean. So i.e., in the past, we were learning about numbers. It'll also ask a lot of questions about horizontal lines, diagonal lines, stuff like that. But if you're trying to classify a picture as a cat or a picture as a dog, the model will learn to ask, does the animal have floppy ears? Now that's a high level representation. That'll be down the line in the convolutional chain. It'll build up from there by looking at shape. It'll look at maybe diagonal lines are conducive to a pointy ear, and more soft rounded lines are conducive to floppier ears. Okay, so stuff like that. And there's a lot of success. You can find animal classification algorithms online that are absolutely brilliant, that are up to human level. Okay, we will get in depth into the numbers next week. So we are not going to specifically go into anything that looks like this week. Those are filter parameters. That is how it picks up on shape. We're going to dive into that next week. Okay, so stepping through the layers, this is actually a real convolutional neural network. And this is going through the layers. So these are the first batch of questions. You can see that it's picking up on different shapes. So look at this, top left right here. There's your horizontal line. There's your diagonal line. There's another type of thicker horizontal line. Maybe it's picking up on different colors. We're using black and white, but if there is different colors in the images, it has to be able to concern for that. This is picking up on circles, spheres, maybe there's dots around. This could be picking up on textures and and build up. Layer 2 is putting those shapes together. You can see it's getting a little bit more complicated and complicated. It's combining different features together and creating higher level representations. And at the very end, you're getting very complex shapes. Look at this honeycomb design. That honeycomb design, if you see that in an image, that can be very, very representative of things like, specific shape. If you're trying to classify bees and you see a honeycomb in the background, I mean, come on, that's amazing. On these layers, you'll also see not in this example per se, but if you're trying to train a neural network, convolutional neural networks are good at picking up on text. So if you take a picture of your like check, if you ever do online banking, you can take pictures of checks now, and it'll actually write out your name. These high level things, you'll start seeing like N's and S's and A's and B's and C's and P's, because it's using the shapes from the past, building upon them, and creating representations of letters. Very interesting. They're very cool things, in my opinion. So PyTorch, using them right now. This is what we're going to do. We're going to actually write this exactly. This is going to be in our model. So spoiler alert. We're going to have 3 layers in our model. The in channels and the out channels are what I want you to worry about right now. Kernel size and padding is something we're going to tackle in the future. The in channels are how many questions you've asked in the previous layer. The out channels are how many additional questions you want to ask. So the first convolutional layer is going to take 1 channel in and output 6 channels. So basically, what it's going to take in is the image, the pixel values. We have 1 dimension because we have black and white pixel values. Okay, so you can kind of see the image as a question, because an image is a question. Okay, and that question is there a pixel here? It's a very straightforward question, but it is a question. The convolutional neural network will create filters. It'll create 6 of them. Those 6 filters are your questions. It'll go throughout and it'll ask different questions about shape, curves, circles, stuff like that. Our next layer will take those 6 input questions and create 36 output questions. So we're getting higher level. We're asking more questions. And we'll continue that in our 3rd layer. Finally, we'll have 100 questions outputted. Okay, perfectly. We're going to go through that together. The next thing I want to talk about is max pooling. Max pooling can be a little bit of a complex idea, but in practice, it's very straightforward and it's great. It's pretty standard for convolutional neural networks. Okay, so max pooling. Surprisingly, it is a different thing than convolution, but it looks very, very similar. What max pooling does is it'll create another map. Max pooling goes through the entire next in chunks. Oops, the entire image in chunks and always keeps the highest max score. So just like this, it creates another filter. It'll convolute through the entire image just like before, but instead of asking a question, it'll do something very programmatic, very simple. It'll just take the highest value. So these 4, we have 4 no's, the highest value is a no. We have 4 no's here, no. 4 no's here, no. And then no, no, no. When it gets interesting is we have some yeses here. So this, for example, this image right here could be our question, is there a horizontal line here? And this could be our 7 again. So we have a bunch of horizontal lines right here. So we basically have a straight line in the picture. And we max pool. We always take the max values. Yes, yes, yes. And we continue. We see a bunch of no's down here. No, 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 no. Okay. So we've transformed this high level. This is an 8x8 image. And we have transformed that into a 4x4. So why do we do this? Why do we do this? What we do this for is it helps to reduce redundant data. So if you are a convolutional neural network, you are interested with horizontal lines. You want to know where they are. You don't really care about where they are not. So you always take the highest value, and that is going to be conducive to different image features. So for example, our 7 with our horizontal lines, it gets rid of a lot of redundant data. It keeps all the interesting ones and reduces a lot of the no's. And it also keeps general shape. So you can see here, we had a big horizontal line covering right here. It keeps that shape in this max pooling reduction. Okay, so it just reduces dimensionality. It gets rid of unnecessary data, makes it run faster, which is all grades, all grades. So here's our model. What we're going to do is we're going to take an input image of 1x40x40. We remember why. We have 1 black and white channel, 4 pixels high, 40 pixels wide. And we're going to have 3 convolutional layers. We're going to start with 6 questions, then 36 questions. And at the very end, we're going to have 100 different questions. We're going to pass that into a linear component, which starts with 3,600 nodes. We'll see why that's 3,600 nodes. It has to be 3,600 nodes. We'll get into that. Then it goes to 1,000, 500, 100, and the output of 8. Important number, 8. That is something we're going to go into, and we're going to learn a little bit about. That's what it looks like. Why did I choose these specific numbers? There are general rules, not rules. They're very flexible with these things. If you use different number of questions, for example, if you did 3, 12, and then 50, for example, you will still get results, and you'll probably get good results. You might get slightly worse results. You might get slightly better. It's hard to really say that this is a good outline for a model. This is a bad outline for a model. It really is. It's just about testing it, training it, and seeing what's best. There's certain tips and tricks. So what we want typically with a convolutional network is to start with a small amount of questions and keep growing and growing. And then we also want to reduce our dimensionality. So each step we're actually max pooling. So we go from 40 by 40 to 20 by 20 to 10 by 10 to 5 by 5. And that is through max pooling. That's one of the rules that you want to go with. Linear layers, there's the same idea. You want to start big and go smaller. Is general, but that is what they'll teach you in class to do. It's usually where the best results are. But I'm going to say these models are very fluid. I really suggest you guys changing around these variables, seeing if you guys can beat my score, because this is what I trained it on. Okay, so convolutional neural network 1. Okay, so this layer right here, this is number 1. This really skinny one, that is our image. Our first question block is going to ask questions like, are there any horizontal lines here? Are there any vertical lines here? Circles? Is there a hair texture like I talked about before? What color is the hair? It's going to be either black or white in this, but if we use color, it would be asking those questions. And what color is the skin tone? That is conducive, of course, to guessing about ethnicity. Building upon that, we're getting a little bit more difficult. What type of texture is the hair? It can start really be more detailed. This is curly hair versus this is straight hair. Is there a protruding jawbone there? Which, if you're really building upon, that is a strong indicator of a more masculine face in general. Everything in here is in general, and you're actually building upon a lot of generalities and coming to an okay solution at the end, instead of having very discrete yes or no questions. Is there flatness in the face? Flat faces are found in babies. Are there wrinkles? You guys should know wrinkles are, pretty famous for being on older people's faces. And then convolutional neural network 3, we're getting to the really high level, interesting questions that are very strong at determining gender, age, ethnicity. How chubby are the individual's cheeks? How long is the person's hair? Are there any wrinkle textures around the eyes? So if your linear component right here, which is your last question set, is going to output to a linear component. If your linear component is being fed in answers like, this individual has chubby cheeks, no hair, he's bald, and has no wrinkles, that's probably a baby. Okay, that's most likely a baby. If it has a lot of wrinkles around the eyes, you're probably dealing with an 85-year-old or an 86-year-old or someone quite old. So you can see how the neural network can bridge those gaps and come with great solutions through the work that is done through the convolutional neural network. Okay, our loss function, you'll see why. We're getting a little bit creative with these loss functions. Okay, so our input, we're going to patching in, and remember mini batching. I'm going to talk about this again. We're going to run through 32 images into the convolutional neural network at one time. All of those images will be one color dimension, 40 by 40. We'll pass it through. The model will do a bunch of math. This is a big function, a big mathematical function with a bunch of parameters. Once it's done that math, you'll get 32 So you get 32 in, 32 out, always, that never changes. And then 8. So you get a matrix that is 32 by 8. And that 8 is because, you'll see why. But 8 is the interesting number there. Okay, so this is why. We have a table that is 8 long, 1, 2, 3, 4, 5, 6, 7, 8. And that is because of our problem set. So we are trying to solve 3 questions in one. Before, I was usually getting you guys to solve 1 question. We're actually solving 3 at the same time. We are solving age, which is a regression problem. Okay, so what I mean by a regression problem is a person can be any age from 0 to 85 in this set. You could be older in real life, obviously, but in this set, it's 0 to 85. And that means it is regressive. Okay, there's not distinct buckets. We're going to be treating this as a number. So just like price is a regressive number, you can have, you know, $25.83. We're be treating age as a regressive problem as well. So much like our cow and diamond examples from week 1 and 2, a regression problem asks for mean squared error. That is our loss. So remember, we have our predicted value and our true value, and we're trying to smush those together to make them as tight as possible. That is a good prediction. And mean squared error smushes them together. That is our goal. Okay. Gender. Now, this is a different problem. This is a classification problem. This is much like our numbers, our number buckets. Before, we had 10 different numbers it could be, 0 through 9. Now we're going to be talking about being male or female in this set. Obviously, their gender is a fluid construct. In this, everything is labeled as male or female. Okay. Ethics. We're going to talk about that at the end. Okay. I'm saving it all for the end. Ethnicity. In this classification set, we have 5 different ethnicities. We have Black, Asian, white, Indian, or Hispanic in this set. We are classifying much like our handwritten image set. We need a softmax loss. So our classification problems need softmax losses. So our vector of length 8 is a bunch of different values. And these values are split into our different classifications, okay? Or also regression. So the first thing is MSE age. So that is our mean squared error for age. That is the loss function we're going to be using. So our age, you can see right here, it's between 0.78 and it's the value 0.78. It is a number between -1 and 1. It is normalized. So remember, when we're talking about normalization, models like small numbers, if you want the number 85 as an output, it causes issues. So what we do is we normalize that. So the min value, it will be -1, and the max value will be 1. So an 85-year-old, we are going to translate that number 85 into the number 1, because that is our max value. And then a baby who is age 0, we have a bunch of age 0 newborn infant pictures, is going to be classified as -1. So but it keeps that distribution. So someone who has a normalized age of 0 is actually somewhere in between 0 and 85. So they're a middle-aged person. So a value of 0.78 is an older person for sure. That person is probably 70, 75, around that age. We've been talking about our softmax for gen, that's softmax for gender. We can see right here, our model predicted that there's a 98% chance that this is a female and a 2% chance that this is a male. And it's going to do the exact same thing with ethnicity. So softmax F. It believes 88% that this person is Asian, and the other ones are lower amounts. Okay. So our loss, this is where it gets interesting. Remember, our loss is just a mathematical function. So what we can do is we can combine our losses together by just adding them together. So our loss for our model is going to be mean squared error for age. That is our age loss. Our softmax for gender, that is our softmax or gender loss. And then softmax for ethnicity. That is obviously your ethnicity loss. You add those together. I want you to notice that adding functions together makes another function. Okay. So one of the criteria for a loss function is it has to be function. Bingo, done it. We can also see, and the important thing is that low scores in MSEH, softmax gen, and softmax F leads to a high total loss. A low total loss. This is an old slide. Okay, I should have been doing a more recent one. But essentially, what you're saying is If age MSE, softmax gen, and softmax ethnicity are all low, our total loss is low. And our goal is to lower all of our losses together, and that'll create a low overall loss. So the goal is the exact same. We use it in the exact same way. We're just having a nice little cheat, essentially, to do a bunch of different tasks in one. Our job is still to minimize loss. So we have a valid loss function, and it's a very smart way to do it. And it is used in a bunch of different domains. A lot of times people have different types of losses and they combine them in a linear way. So that's what we're doing right here. Okay, great. So you can see right here our example. If we have our prediction on the left, this column right here, and our ground truth on the right, this is an example of a good classification. So our model did a good job. It predicted that this was a normalized age of 0.78. And the truth was it was 0.77. So very, very close. It predicted about being, this person is probably about 75 years old, and they were 75 years old, essentially. Gender, the ground truth, it says that this is a female, and it got it right on. It said 98% chance that it's a female, and they got it right. Ethnicity, this person was a person of Asian descent. The model predicted it bang on. 100% got it. Actually, not 100%. It got it 88%. But it did a very good job. So what that means is MSE age. We can calculate it right here. This is our mean squared error formula. We take predicted minus the ground truth, square MSE 0.0001. Very small amount. We didn't get into softmax loss, also called cross entropy loss. I know I've thrown that word around in the past. We haven't gone into the formula. It's a little bit involved, but we know how to use it. And we can see that we have a very small amount for our gender loss and a very small amount for our ethnicity loss. It's a little bit higher, but asking ethnicity is a harder problem because there's 5 columns or 5 different ethnicities to choose from, while in gender there's only 2. Okay, but we add those all up together, our total loss, and we get a small total loss. We actually did a very good job classifying this. This is an example of a bad guess. So the person being 75, our model predicted them being about 15, probably. Negative 0.23 is about probably 20-year-old, actually. It thought about 50% chance of being a woman, 50% chance of being a man. It had no idea for this disease. It thought it was like 20% everything, essentially. So we can see that that leads to a high loss. So the problem is the exact same. We want to minimize our loss. Okay, batch normalization. Here is our one slide that we're going to go into for batch normalization. Okay, batch normalization is very important. It is, if you read a lot of the academic papers, they like to throw around words like groundbreaking and revolution, big things. It solved a lot of problems in machine learning. There's issues called exploding gradients. There's something called a vanishing gradient. There is normalization issues. These are very involved mathematical terms. The paper is very hard, very complicated to read. But you just have to know that it's one of the best ways to make sure data passing from layers to layers are normalized within a certain range. This can prevent models from having exploding gradient issues and allows the model to train faster. So model trains faster, gets rid of a lot of issues. Essentially what it does is, if you want to know a very simplified version, is it takes what can be a cacophony of different outputs. Layers can produce a lot of different crazy outputs from one end to the other, and it normalizes them to fit inside a Gaussian curve. It's a complicated process. I don't quite understand it. A lot of professors don't quite understand it, but you just need to know that it works, and it's brilliant. It solves a lot of issues. And the thing about PyTorch that we're using is it makes it so incredibly easy to use. It's trivial, and you basically just add it at the end, activation of each layer, and use it in conjunction with nonlinearities. So we can see here in the code, our batch normalization is right here. So convolutional neural network 2 underscore batch normalization. All we did was rewrite nn dot batch norm 2D. That's it. Awesome. I think we got a question. So do we not need to normalize the values out of the data set when we use this? We still do. We still do. In general, it depends about what data you're putting into, But if you're putting in data with extremely high values or extremely low negative values, it'll still create those same issues. It is a tool to fight against that. It is not necessarily perfect. Normalization is standard, essentially. So we do have to continue, but that is a great question. Okay, so moving forward, this is something I want to talk about a little bit. It's a new type of non-linearity. So remember 2 weeks ago, we talked a lot about sigmoid and what that meant for a model. We are changing it up. We're going to use something called ReLU, which is called a rectified linear unit. It's just a different non-linearity. It has nice mathematical properties. We're going to be talking about it more next week. We're going to go more in depth. It kind of goes hand in hand with convolution, interestingly enough. But you can see that it looks quite similar. We're gonna dive into that in a little bit. Okay, awesome. So model limitations in ethical computing. This is what I want to talk about a little bit, okay? And understand responsibility as deep learning engineers. Okay, so the two main issues I want to talk about are training in the data set and deployment. So first of all, we have trained a model on a data set, okay? Obviously, we need to train it on a data set. Without the data set, it won't learn, but the data set can have a lot of caveats to it. A data set is not necessarily a good representation of the population, okay? So we have gone over this before. We have a model that knows about men, women, and a designated handful of racial groups, okay? And that is the big keyword is designated, okay? It cannot discern between people, for example, of Polynesian descent. We haven't trained it on those groups of people. So if you have a company that uses this model to give out, for example, government grants, right? It takes in images and maybe they're using it for good reasons. They take in images and they want to make sure that they're not having racial bias in their data. So they can see that this is an African-American individual, and this is an Asian individual, this is a white individual. They want to make sure in their data that each person is getting the same amount, no matter what race they are, okay? So discerning between gender and ethnicity is a scary topic. It can be used in good ways. It is an important problem. It's a problem about people and about life. And those are the scary types of topics that a lot of engineers are trying to tackle. We have to use it responsibly, okay? Right, so if you're making a model that's trained on 5 different ethnicities, if you pass in a person of Arabic descent or something else, they could be mislabeled, they could be not shown up at all, they could be left in the dark, okay? And also when we're training this data, what if we train it on 1,000 pictures of men, of white men, and 10 pictures of Black women, okay? In our data set, if there is bias in the data set, the model picks up on the data set. It'll get that bias in the models. There are examples in the past, very real examples, very scary examples of they tried to use image data set to try to find out if a person was guilty before, okay? So this is a real case. There is an idea in history that is not really actually founded in science that you can tell when someone is lying to you by the way that they look. You ever hear the idea that if you look in the bottom left of your eye, you're lying. If you're looking in the bottom right, you're probably telling the truth. It's complete malarkey. Whoever told you that is lying to you. But there is an idea. Judges, one of their main jobs is deciding bail. So if they trust an individual who's committed a crime or is under investigation for committing a crime, they can put them in jail, or they can give them a bail, which they have to pay a certain amount of money and they can go free and then they'll get that money back, okay? But they have to make that decision based on trustworthiness, okay? So judges do a bad job at discerning if that person is going to go out in the world and commit more crimes and they should probably be locked up, or if they're totally fine to go back, they'll come back to court for their bail. They do a bad job. So what a bunch of researchers tried to do is they took pictures of faces, actually video specifically, and they looked at those models and they tried to look at body language to see if this is the type of person that would come back for bail. Maybe they're they're more angry, and the model can pick up on the person being angry and not coming back. But if the person is like put together and smiling and respectful, the idea was that maybe they can go out for bail. They're a trustworthy individual. Okay. When they created this model, they used labeled video about the trustworthiness scores from judges, and they trained that model on it. So they had these great ideas about body language and trying to find out if that can lead to a good prediction of whether this person is trustworthy enough. What the model did do, however, unfortunately, is it picked up on the person's race. It learned what race a person was and deemed African-American people as less trustworthy than white people, because it wasn't the fault of the model. The model is programmatic. It did everything it needed to do. The issue was that there's racial bias in those judges, and those judges labeled certain individuals as less trustworthy depending on race. Okay. So if you feed in ethically questionable data to a model, that model will take it and it'll run with it. It is our job to make sure that we are training our models, we are teaching our models to do good and to ignore those biases that have plagued us in the past. Okay. So big, scary question. Big field coming up. Okay. I've talked to a bunch of researchers. I have a friend at Oxford University, okay? And he's in deep learning engineering. And I sent him an email and say, hey, I'm interested in getting into deep learning. What are some of the fields? What are some of the stuff? He works in robotics. He said, the big field, the question that a lot of people inside the field are trying to figure out is ethics. How can we make this work for people instead of working against people? Big field is very scary. There's no real answers so far. So not too scary, but the other thing is deployment. Okay, so I talked about training and the data. The deployment is deep learning is a powerful tool. Okay, and this is getting more and more into the future as deep learning gets better and better and better. We have to ask, what are we using it for? Okay. So we can use the algorithm for good or bad. We are using an algorithm that can discern between gender and race. Those are both very, very scary topics, and we can use them in bad ways and we can use them in good ways. We can use it to fight racism, to fight sexism, or we can use it to propel it. Okay. The same technology used in self-driving cars is used in autonomous flying war machines. The facial detection can open up your iPhone, and it can also use to track people on the streets. Okay, so it's a human decision we have to make, and one of those ethical conundrums. Okay. So a little bit of a scary topic. This is what I'm talking about before about discrimination in the data. We have a lot of babies. We don't have a lot of training data about 90-year-olds or 100-year-olds or 116-year-olds. So if you are a 116-year-old, you're not represented in the data. Another issue, there is a lot more white people in the data set, which is unfortunate. It's one of those things you have to look out for. There is not too many where it's an issue. In this case, you know, these pictures, a lot of these pictures were taken on college campuses in America and of celebrities and stuff like that. That's where the data is coming from. And most people in America are white. Right now, it's getting more and more culturally diverse, but we got to make sure we're training them properly. Okay, so that is just one of those topics that I wanted to go over. In machine learning courses, they don't usually talk about ethics of computer science, and I think that's a misstep. Something you should read about, you should prod against, and it should always be in the background of your mind, because you guys are, we're going to be starting to move with fire. If you continue learning and educating yourself in deep learning, you become a deep learning engineer, you are going to have to run into questions like this. Okay, and this also extends to, this has found a home in deep learning 100%, but it also extends to traditional programming as well. People at Facebook and Google and stuff, Facebook knows that they're causing a lot of issues in the world, and it should be their responsibility to clean it up. I don't know if they are right now. Okay, a little bit of a scary topic, but something I wanted to go over. Okay, so we are going to get into the coding right now. Okay, we're going to be doing quite a bit of coding today. This is a little bit more of a involved coding session. GitHub.com, once again, /BrainTank. We've done this before. BrainTank deep learning. Here we are, week 4. We're getting there. How exciting. Should see this. Okay. Sorry, talking so long, it knows my throat, makes me cough a little bit. Same thing, easy peasy. We're gonna download it. I'm gonna be a little bit faster this time because we've done it before. Okay, saving that. Open it up. Go folders. Extract it. Extract all. I'm gonna once again just put that on my desktop. So it's there. Desktop, format, great. Okay, awesome. Here it is. There's the folder on the desktop. Spelled it right this time. No errors. Going over to collab.research.google.com, or if you just put in Google Colab, easy peasy. Right there. There it is. Google Colab. We all have the data set going, everything perfect. Okay, we're gonna create a new notebook. I'm actually gonna switch over to this account. Okay, we're all gonna create a new notebook. Awesome. You guys actually shouldn't be able to see my files because I'm just showing my internet page, but I'm sure you guys all know how to do now. Upload notebook. Okay. If we're lost at all, let me know. You guys should remember though. I'm going to my desktop. I don't think you can see this right now. Oops. Fix that 1 second. Okay, just take a second to set it up. I'll be waiting. Okay, cool. So once you have that, you can model, you want to put in week4.ipybn right into there. Awesome. And once you do that, you should have something that looks like this, okay? Let me know in the chat if you're having any issues. You should be used to it by now. Okay, great. I'm gonna assume that you guys are all ready, unless you say anything against the fact. Great. Okay, so going over it, just like last time. First thing we gotta do, this one's there's a little bit more code, but we're essentially just cloning again. We're gonna run the cell. We're gonna wait. It'll take some time. It's gonna be downloading a bunch of stuff. What it is downloading is, I'm sure you guys have all used Git before. Git has an extension called LFS, or the large file system. Because we were working with so many images, it's about 200 megabytes of data. And typically GitHub doesn't like that. But if you use Google or GitHub large file system, LFS, it works. So that's how we're getting our data down here. So it's downloaded. Great. Brilliant. We're happy. Let's take a look into it. Week 4, what do we have? Age, gender.csv. That is the big file, the big interesting one. Let's double click on that. We can see the file is too large. Can't display it. So good. But that has all the information about our research. Okay. We have model.state. We're going to get to that in a little bit. That is my pre-trained. I've trained this for you because it takes some time. And then over here, if you look at it, these are our answers to our code. So if you guys are struggling, I totally recommend you guys look at this. You can take this home. This will be published. This already is published on the GitHub. So please feel free to cross-reference. Okay. I have a bunch of, once again, I have a bunch of helper functions. So here is our data set loaders, and here's our data set up here. Did that for you because we were working with CSV files. We want to transform that to images. Displaying data, we'll get to that. Here are our two losses. We want our softmax loss and our MSE loss. So those are done for you. And then creating ground truths, that's just a helper function. Okay. The next thing I did for you already, because it is quite annoying to do and it's not very complicated, is I did the test for you. So we're going to work on training the model. We're going to be working on setting up the model. We're going to train it and then we're going to test it, but the testing is already done for you. Okay, so we have our test function. Perfect. Okay. I hope we are ready because we are getting into it. Okay, so first thing as always, I think we should set up. We're going to check out the data set. Brilliant. So actually, before we do that, remember, we want to go up to our helper functions. So here are helper functions and run them. So they're usable. In any other case, we wouldn't be usable. They would not be usable. Okay, so we run it. It takes some time, basically compiling the code. Python does have a compiled version to it. You guys didn't know, but that's what it's doing. It takes some time. La di da di da, la di da di da. Weather's been nice. Okay, awesome. That's ready. So that's run. Okay. I also have, so these are our labeled translations. We don't really need to use them that much, but just remember for our gender, a 0 is a man, a 1 is a female or a woman. And here are ethnicity, same thing. Okay. So first of all, let's get that data set. So we're going to have our train loader or train data set and our test data set equals, and a function I created for you is create data loaders. Okay, so we just do this. And talk about this in the past. Python's pretty cool. I know C doesn't do it. A bunch of other languages do it. C doesn't. So if you're just used to C, you're not really used to it. But Python actually has the amazing ability of returning. You can return multiple values in a very easy, simple way. So here we go. We're returning our training data set and our test data set. Let's run that. See if it works. See if we're getting errors. Okay, running the code for the first time, it'll take some time because what it's actually doing, and we'll get to it, is if you press refresh on this folder right here, right there, perfect, and open it up, it'll take a second to load. But what we were doing is we were taking all the data from the CSV file, which is essentially an Excel file, and that Excel file has a bunch of pixel values in it. And what we were doing is we're transforming that into actual images. Okay, so there we are. Here we go. Here are the images we're working with. So here's image 0000. It is of a baby. In fact, we're only going to get pictures of babies because Google Colab will only, inside of a folder, will only print the first 1,000 pictures, and we have like 1,000 pictures of babies. So we have a lot of babies, but we'll see in the future that this isn't just full of babies. We have a lot of images. We have 27,000 specifically. Okay, so that is what we've done. We have it working. Let's, as we call, iterate throughout it. So let's just test out. Let's just prod a little bit into the data set and let's see what happens. So I'm going to do 4, and then it's going to be patch. So this is our mini batch in train data set. Okay, and we're going to print out what our batch is. So that's going to get every batch in the data set. I'm actually also going to break after it, so it doesn't print out a million different things. It'll just print it out once. So print out the first batch. Great, here it is. Here it is. Here it is. Here it is. So we have different things. We have the age tensor. We have 32 different normalized ages. So I did the normalization for you because I am such a helpful person. 1.5071. That is a very old person. Wow, wow, wow. All the negative ones are children or people under the age of 35. Negative, for example, what's a very high negative value? I don't know, negative 0.4, that's quite young. Okay, we also have our ethnicity values. So remember, if we look at that, 0410030, those are all, the zeros are all our white people, the 1 are African descent people. Black people. Number 2 are Asian people. Number 3 are Indian people. Number 4 are Hispanic people. Okay, that is the races we have in our set. We have gender, same thing. 1 are female, 0 are male. And then underneath this big scary tensor looking thing, those are our actual images. So we have 32 different images. So let's actually just take a look at them. What I'm going to get you guys to do is we're going to get images equals batch. And what it is this is actually called a dictionary. I'm sure you guys are familiar with dictionaries. This is a Python dictionary. So we can grab our indexes, our age string, or not our age, oops, image. So that is our images. Those are 32 images, and 32 is our batch size. We'll get to that. Our ages is batch age. Okay, oops. Brilliant. Our gender, I'm just gonna call gens for the entire thing. GENS, okay? Just so we can save some time, save some space. Gender, and same thing with ethnicity is eths equals batch ethnicity. Okay, now what I want to do is don't print out the values. We see the values, what they kind of look like. Let's just see what they're shaped like so we can actually start using them. Images.shape. We're going to be doing a lot of typing today because for basically everything, we're going to have to type it out 4 different times, but it's okay. It's good practice. Pages.shape. Actually, I'm gonna put that first, just so we have the coherent order. And then we'll always have S last shape. Okay, so now when we're running it, we run la-di-da-di-da. Great. So what we have is we have our 4 different, we have our one feature. This is our input. So remember, features are used as inputs. And then are 32 images. And like I said before, our images are of dimension 32 by 1 by 48 by 48. 48, I thought it was 40. Okay, I was wrong. My entire PowerPoint was very incorrect. Our images are 48 by 48. Interesting, good to know. I thought it was 40 by 40. Okay, interesting. So 32 by 1 by 48 by 48. So we have 32 in our batch size, 1 black and white dimension, 48 height, 48 width. Brilliant. Our ages, we have 32 different ages. So it's just a list of all of our ages. So each image in our batch will have an age associated with it. Same with gender, same with ethnicity. Great. So enough with that. Let's actually get printing with it. Let's actually look at some images. So I have created a function for you. I've created 2. We're gonna have to use 2. So display data. Awesome. So we're using display data. We can put in our images. Okay, we run this, should work. It's going to print out. So we have a batch size of 32. It's going to print out the first 9. So here are first 9 faces. How beautiful are they? If you look, when we look at a lot of these, try to pick out the celebrities because there's quite a few celebrities in here. And babies and old people. There's a bunch of different looking people. It's kind of fun to look at the celebrities. Okay. Now, if we want to actually display the images with them, with the labels with them, what we can do is I made another function called create bunch. Create bunch is very easy. We're going to call it our target, or this is our ground truth. Equals create bunch, ages, and then we just pass in the ethnicity as well. Okay, so our bunches, it's just a helper function. It's there to help you out. It basically takes all those 3 different values and puts into one big tensor. So we can say that instead of like looking at all these individual things, we can just say that this is our ground truth. Okay, so our target is equal to ground truth. Okay, let's also print out what the ground truth looks like, just so you guys can understand. Okay, awesome. So you see before it took oops, printing right now. These are all the ages of the people on the left. Here are all the ethnicity labels, or sorry, gender labels, and then here are the ethnicity labels at the very end. Okay, so now we can see it's added this column up here. It says that this is a 29-year-old woman. Brilliant. This is a 21-year-old woman who is Indian, of Indian ethnicity. Can you just go through looking at all of these? Here you go. Say hi to Zayn Malik from One Direction, I think. Might be wrong on that. I'm not a big One Direction fan, obviously. Yeah, interesting. Okay, so we actually see the images. I think it's kind of fun to prod around sometimes. We're going to save that just so we can use it in the future. Great. Okay, what we want to do next is the scary thing. The big scary, the hardest part of this for sure is going to be defining the model. Okay, so let's create a model. Model equals and I've created the model initialization for you. It's called age gen eth model. It takes in no parameters in of itself. So that's easy for us to do. So it's going to be age, capital A, gen eth model. There we go. We've created it. So remember when we create our models, first thing we want to do is initialize it. This is where we're going to put all of our parameters. And it's basically all of our layers and all of our helper stuff. This is going to definitely be the longest one you've ever seen. The other ones were quite easy. This is going to be a lot longer. So we have to write convolutional layers. We have to write linear layers. Remember, our convolutional layers feed into our linear layers. And we're going to write in our helper layers. Okay, great. So we're going to start with our convolutional layers, and then we're going to dive into some helper layers. Great. So I'm going to be, instead of writing all the parameters together, I'm actually going to do in conjunction with our forward pass. You'll see what I mean. So the first thing we're going to do, self. Remember, we always have to put self. And we're going to make our first convolutional layer. We have to call it conv1. Okay, so when we create these models, make sure that you like all the capitalization is correct. It's the exact same as mine, because if we don't, when we load the pre-trained stuff, which is what we're going to do like we did last week, I pre-trained a model for you, you'll create some issues. But essentially what we're going to do is we can do NN, that's our neural network. That's the exact same thing as torch.nn. Now we can just write NN, it'll save us some time. NN, and how we make convolutional networks, I've said this in the PowerPoint, we're going to do conv2D. Brilliant. Now, what we got to worry about? In channels. In channels equals, we're going to set our in channels to be 1. Remember, that is our number of dimensions in our label, right? So our pixel values. Okay. Out layers, out channels. I chose an arbitrary number. 6 happened to work. I chose 6. Okay. We're not going into this today, but we have to make a kernel size. So kernel size, we're going to be equaling that to 7. And the last thing we got to do is something called padding. Once again, that is a next week issue. But padding is equal to 3. Okay, so to save some time, I'm going to ask you to copy this. We're going to do it 3 times. 1, 2, 3. We have convolutional 1, convolutional 2, and convolutional 3. Now the numbers we have to change. The in channel, remember, it's always going to be the same as the out channel of the previous layer. So we're inputting 6 different questions, and we're now going to output 36 different questions. So our input output. Our kernel size is also going to be 5 now, and our padding is going to be 2. Okay. Brilliant. Our in channels now, remember 36. For our last layer, if you remember from the PowerPoint, it's going to be an out channel of 100 questions. So we're building up, we're getting more complicated in our questions, we're going to have more of them. Kernel size, 5. Padding, 2. Those are our convolutional neural network layers, okay? Now, let's create some of our helper layers. We're going to skip the linear right now. Helper layers. So the helper layers are the things I talked about before. They are specifically our max pooling. So remember, max pooling is our dimensionality reduction, creating an 8x8 image and squishing that into a 4x4 image, taking only the most important parts. We're also going to have our non-linearity. So before we use sigmoid, right now we're going to use ReLU, which stands for rectified linear unit. Another topic for next week, but it works and it's brilliant. Okay, so how we create our max pool, we're going to do self.pool equals neural network dot max pool 2D. You see how easy Torch makes this? PyTorch makes it? And it's going to be 2 by 2. That essentially just means we are dividing all dimensions by 2. Our filter is 2 by 2, and it's going to take all like 4 pixels and put them together, just like we did in our example. Okay, self.ReLU, RELU, ReLU, similar format. This one's even easier to do. ReLU. Remember, look at capitalization of the ReLU. It is a rectified linear unit. That's why the capitalization is like that. Awesome. And the last thing I want to dive into is we're going to have to create a bunch of different batch normalizations. Okay. So we're going to do batch norm 1 equals nm dot batch norm 2D. And what we have to do is we have to put a dimensionality associated with that. So we're going to do batch norm at the end of each one of our convolutions. So we're going to copy our 6 value. Okay, 6, and that'll just normalize our values for it. It'll make it very nice. I hope I'm not going too fast. We're gonna have 3 different layers: batch norm 1, batch norm 2, batch norm 3, and that they're going to be our output dimensions. So the first one, it outputs a 6. Second one, it outputs 36 questions, and the third one is going to output 100 questions. So that's what we're looking at. So now let's start putting some images through it. So what we can do is in our model, we're going to take our images, take our model, and we're going to put in our image. So our images, remember, they're shaped 32 by 1 by 48 by 48. Awesome. And we are going to shove them inside of our forward loop. So we have, these are our parameters, they're outlined for us. And this is our forward propagation. This is where our image is going to go. So before we start, let's just print out the shape of the image to make sure that we got it. Okay. So we run this, run over to the bottom. We can see that when we forwardly propagate, we have a 32 by 1 by 48 by 48. Awesome. That's what we need. It is ready to go into the convolutional neural network. Okay. So we remember how to do that. Image, we're going to morph it in a way where it's going to be image equals self.conv1. So we're calling this. This is what we defined, and now we're calling it self.convolutional1, and we're just going to put our image in it. Okay. We're going to do that for every single one of our convolutional layers. Okay. Great. Okay. If we run this, we should get it works, but it's not exactly what we want. We aren't getting exactly. Let's actually print out image.shape after you. Okay. So now we can see, remember our question started with 1, and then when it goes to the very end, it's at a 100. That's perfect. Our convolutional neural network layers are working, but it's not exactly what we want. We want to add input on some of our helper functions along the way. So how we can do that is, and every single layer is going to be essentially the exact same. We are going to apply batch normalization, pooling, and ReLU. Okay. So it can look a little funky, but it's easy to do. So we want batch norm 1, right? And then inside that, we are going to be putting self.ReLU. And inside that, we're going to do self.pool. And inside that, that's our image. Okay. So it looks a little funky. Looks a little funky for sure. What it's doing is it's taking that image, it's applying max pooling to it. So it is changing it from a 48 by 48 into a 24 by 24. It is reducing that. It's taking the most important parts. After we've done a convolutional layer, it is reducing that. It's taking the most important parts. Then it is applying our nonlinearity. So remember, our numbers could be within a massive range. We're squishing them in between to find our nonlinearity. This one is using ReLU. And then we're putting in our batch normalization. So batch normalization being very complicated. I want you to see this as giving your image, giving your intermediate steps medicine to help it heal a little bit, because there is a bunch of different situations in which you can have issues in between the layers. There's a bunch of different problems you can run into. Pooling, ReLU, and batch norm, those are going to be your tools to help assist and solve those issues. Max pooling, it solves bloat. It gets rid of all the unnecessary values and keeps the important ones. ReLU, that is our nonlinearity. It produces linearity issues, which is another, these are mathematical concepts, a lot of them. And then batch normalization, exploding and vanishing gradient, also it helps speed up. Okay, so we are giving our model some steroids. Let's put that in between every single one of these layers. Okay, the one difference, the only difference is that we're going to change batch norm 1 to batch norm 2. Okay, batch norm 1 to batch norm 3, because there is a requirement of a certain amount of dimensionality. So the dimensions have to be correct. And only after convolution 3 will it be 100 dimensions. Only after convolution 2 will it be 36. Okay, so you don't have to do this. I just want to illustrate something to you guys. I'm going to take this and I'm going to copy in between every single shape. Every single shape. Every single line code. Okay, there it is, there it is, there it is. And we'll see how it morphs. Image.shape, I gotta say, probably the best tool you use in machine learning right now. It really is super, super useful. Oh, we can ignore that. Don't worry about that. Great. So first step, this is our image. That is nothing changed to it. We used a convolution. From that convolution, we got 6 questions out of it. Okay, great. We have an array. Remember those maps that we made, that tensor board? We have an array of 48 different answers to the questions by 48 different answers to the questions. Bloated. Let's reduce that. We divide it in half by 24 by 24. We keep all the most interesting answers. Great. We've done a step. In between those steps, we are applying a nonlinearity. We're applying batch normalization. It's the medicine. Okay. Next, we're ready for the next layer. We do it again. We increase the 6 questions. We take those questions and we learn from them. Is there a line there? Is there a circle there? Is there a diagonal line? Is there a shape? Is there this? Is there that? It builds upon them. It starts bringing out on features. These 36 questions are asking things like, are there wrinkles? Are there an eye shape? What does that eye shape look like? Is it of an old person? Are there puffy cheeks? It's starting to build more complicated things. Those are what those 36 questions are asking. We apply the same thing again, reduce the redundancy. Instead of having a grid of 24 by 24 answers to the questions, we keep the most important questions. We use max pooling. We apply batch norm again. We apply ReLU again, and we do the same thing. We end up with 32. So we have 32 different images. Remember, we're always going to have 32 here. Batches, they stay the same always. They're universal. We're going to have 100 different answers to the questions, and we're going to have 6 by 6 of those questions. So there's 100 different questions, and there are 36 answers to those questions, locating on different parts of the image. Okay, so we can find out where those eyes are, and maybe that's conducive to some information about the human. Okay, great, brilliant, awesome. Okay, so we've done that. The next step, I'm going to keep all these print statements because I like them, is to get it ready for our neural network layer. But remember, our neural network layers, they work in vectors. So we want to have 32 vectors or 32 just lists. So what we want to do is image.view. View is what can string it out. So we're taking those big blocks. We're taking our 100 by 6 by 6 answers to the questions, and we're turning them into a big string. So we take out 32. So that's the same shape. And then we want it to be 100 by 6 by 6. Notice these, 6. Notice these multiplication signs, right? And we'll see how that affects some things, okay? Great. So we'll run it again, and we'll see the big change. Oops, view. We have to keep that as return that. It returns it. There you go. Image equals. See how change it. Awesome. There it is. So now we can see it took a convolutional block. Remember, if we look at our images, or we like to look in blocks. So here is our, we have 32 of these batches. There's 32 blocks, 32 of these different blocks. Think about that like that. It is 6 by 6 and 100 deep. And what we did is we string them out and we got it ready to be a neural network like this. Okay. That is what we did. We strung it out. So it is strung out. It is ready for a neural network. And let's do that neural network right now. Let's create the parameters. We skip the linear layers. We're going to create them now. So these have to be called self.linear, and we're going to have 4 of them. We're going to have linear 1, self.linear 2. We're going to have self.linear 3. Deep learning engineers are really good at counting. They have to do it all the time. NN dot capital L linear. We're going to use PyTorch's linear instead of our own that we did last time. Now, input dimensions. How many dimensions are we inputting into this? Oh, wow. You guys are so smart. 3,600. Bang on. Those are all of our questions. Those are all the answers to our questions. We flattened them out and now we're ready. And then remember, our neural network, if we look at the shape again, it goes 1,500. What is it again? 1,000, yeah, 1,500. And then this goes to 100, and then it goes to 8. Okay, so those are all of our layers. I'm going to copy and paste this because we are kind of running out of time. We're getting there. Should be a little bit faster. Awesome. So we can keep that, and then we can just change the dimensions. So remember, it has to keep the same. The input is always the last. 500 and 100. And the last one changes from 100 to 8. And we remember why it's 8, because that is our dimension that we're going to be using to for a ground truth. Okay. Great. The next thing we're going to do is not only convolutional neural network layers that need batch normalization. Linear layers can get them as well. They come in a little bit of a different shape. Okay. So instead of doing batch norm 2D, we have batch norm 1D. How amazing is that? Okay. So it has to be called lin BN1. So linear batch normalization 1 is NN dot batch norm 1D. And it's the same thought process. Okay. Start with 1,000 self.lin BN 2 batch norm TD or 1D. It's gonna be 500, and I hope you guys aren't too mad at me that I'm copy and pasting this, because we're gonna use 3 of those. 100. Great. Okay. We have our linear components ready. We are ready to use them, and we have our helper functions also ready to assist. Excellent. So we've done our view. Now, let's do our linear components. Our linear components are ready. So self.linear 1, and we're going to feed in our image to it. Okay. Another helper layer. After every single layer, we're going to do helper layer. Self, we're going to put our self.relu. That is our nonlinearity. We're also going to put in our self.lin, so linear batch normalization 1. Okay, so we're going to put that as our image. Our image will be batch normalized, and then it'll be relu. It doesn't matter what order it's in, honestly. The one thing it's not doing anymore is it doesn't need to be pooled. Okay, pooled is a convolution only operation. So let's do that again and again. We have a couple more layers. Okay, so now we're doing linear 2. We get down here, we're going to be putting our linear batch normalization 2 with our dimensionality of 500. We're going to be putting our relu through there. And then we're going to take that, put it through linear 3, put the image through there. Batch normalization 3. You guys are so cool. And then image equals self.linear 4. And we are not going to do any helper functions after. That is our output. Once we get to our output, we want to treat our output a little more specially. So I am going to, just to continue, I'm going to show you how it propagates through the net. Great. So this is it going through its linear batch. Okay. So we strung it out. Then we are putting it through a linear layer, and you can see it's getting smaller and smaller and smaller. We go by 32 by 3,600, 32 by 1,000, 32 by 500, then 100, and then 8. Great. So we have what we need. Our answers are in here. This is our predicted score. We're going to break them up in a special way. Okay. So remember, I want you guys to forget how we used our model. We broke it up. We took our output. This is our output. You see how this is 8 long? We break it out into pieces. So this is what we're going to do. We're going to break it out into pieces as well here. We are going to take our age scores. It's going to be equal to the image. Take this colon. It means we're going to take all 32 batches. So from every single of the 32 batches, we are going to take the first. So what we're doing is we're taking the first component, which is our age. Okay. We're going to be running age MSE on it in a little bit. Okay. We're going to do the same thing for gender scores equals image. Take all from all 32 batches. We're going to be taking from index 1, and it's going to be until the length of 3. So it'll actually take these two. So it goes from index 1 to 3, but 3 is non-inclusive. So that's how it works. Great. And then finally, ethnicity scores equals image colon, it's all 32, 2 to the very end. So there's 8. Great. Okay. So let's print out those as well, just to make sure that the right size, everything makes sense. Now I'm going to print these all out. Again, you guys do not, feel free to not write down if you guys don't want to write down, print out all the shapes. I'd recommend not. It'd be a little bit of a pain in the side, and I got it all for you. Okay. So great. Here it is. We have 32 age scores, which is great. We have essentially two different gender scores for each image in the batch. We have 6 different ethnicity scores for each gender in the batch. 6. Wait, the right number. Yes. Yeah, we're good. It's okay. That worked in my example. 2, 3. Should be this. Okay, we're gonna keep it as 2. Okay, perfect. It's all good. Okay. Now the one thing we have to do on top, okay, is if you remember, if we print out the values of our gender score. Oh, that's not what I wanted. Gender score and our ethnicity scores. So just for gender and ethnicity, because those are our classification problems. We see that there's a lot of negative values, but these are supposed to be percent values. So just like we did last week, we're gonna have to apply some softmax to it. So those will look a little different after. Okay, so next song, we're moving on. We're gonna call gender scores equals, and then dot functional dot softmax. And we're going to input our gen scores. So it's going to take our gen scores, and then we have to do it as dimension 1. Dimension 1, meaning that it'll do softmax across the gender column instead of across the batch column. The same exact thing for ethnicity scores. Okay, and let's see how that changes. So as you guys are writing that out, I am going to print those out. Cool. So before, we can see that there's a bunch of negative values, and they weren't very nice to look at. Now, these values always add up to 100%, or they add up to 1, but they're essentially 100%. So what these are going to look like in the future are supposed to be 100% female, 0% male. That's what we're trying to get to. If it's a female, we want to print it as a female. Same thing with here. These are different ethnicity scores. Those should condone to the right ethnicity, the right score as well. Okay, great. We have just created our model. So you see how much more intense this is. It's a lot more for sure. We're going to return those scores. So we're going to return them independently. We'll return the age scores, the gender scores, and the ethnicity scores, and they're all ready for us. Okay. I'm gonna get rid of all these print statements. We don't need them anymore. They're gonna clog up our training loop. Okay. Oopsies, don't want to do that. Hey, but I've made no typos yet this week. It's good. Not too many errors. Okay, awesome. That's working. Next step. Easy peasy. You guys are used to this. We don't really need this anymore. We use that for testing. So I'm going to get rid of that. Okay, so just to clear it up. Defining the data set. We're now defining the model. Now, get it over here. Next thing we want to do is define the optimizer. Okay, so optim equals, just like we did in the past, nothing too crazy, torch dot optim dot atom. We're going to be using atom again. So we pass in our model dot parameters. Okay, awesome. That's what we want for our atom. Okay. With that, let's get training. So we're going to call our training function. Train. Training function is our model, our training data set, and our optimizer. So let's pass those in. Train data set. Model. And our optimizer. Sorry, guys, I'm rushing through this a little bit. I've been taking a little bit too much time. I hope you guys are keeping pace. I know you guys are. Okay. So we are going to train for, so I'm going to dive right into epochs because we're going to have to train them over multiple epochs. For epoch, so epoch number, epoch is just number. It's how many times we run it over the entire data set in range, and we're gonna have range 1 to 51. So that basically is going to be, there's going to be 50 epochs. It'll start from 1 and go all the way to 50. That's what that means. So we're going to define our total training loss. This is to find out the average over the epoch. We've done this before, but we're also going to extend that to look at the individual losses as well. So that those are age losses. So 0. So that is going to be MSE. That's going to be our mean squared error. We're going to have a softmax loss for a gender, so because it's a classification problem. We're going to have, for ethnicity problem, we're going to have another classification problem. So it's going to be softmax, and we're going to get to that. We're going to see how that works. So for our batch in train data set, this is looping over every single batch. So our batches are 32 length, and we have a bunch of images. We're used to them. First thing we do, we tell, we'll say that to the end. It's okay. Just like before, images equals our batch. We're going to grab our image. So that's our image tensor. Ages equals batch. We're going to be grabbing our age. Our genders, I'm going to call it gens, is our batch. Inside that are our gender. And then ethnicities. Grab inside that, we're going to be grabbing our ethnicity. Great. So I have a nice little function for you guys. It's another one of those helper functions. So we're going to be creating our ground truths. So gen GT, age GT, and ethnicity GT. That's going to be equal to, where I'm using the function create ground truths. We're going to be passing in our ages, our gens, or genders, and our ethnicities, Fs. Okay. Let's see how that gets everything going. I want to print out its shape. for each one of them. Oops, GT, keep the gender, ethnicity, and then we're also going to print them out without the shape. We're just going to print out the entire array just to see what the numbers look like. See if they're any interest to us. Spoiler alert, they will be. Wait, oh, let's, before we do that, just so we don't print out a billion different things, let's break. And we actually want to break twice. Because it'll break the epoch and it'll break. So we'll just run it once. Break outside loop. That should not be right. Oh, yeah, sorry. There and then there. Agent model object not iterable. Okay, let's see what we did there. In train data set, I see what we did there. I see what we did. I put these in at the wrong order. So the fix to that is we put our model in first and then our train data set. There's the big error number one for the day. Okay, let's see. Awesome. We got exactly what we're looking for. So let's see what happened. Here are the shape for our ages. So if you look at these are our ground truth ages. They stayed the exact same. They actually didn't change at all. They're normalized. Negative 0.9714 is a child of 1 year old. I know that for a fact. A high value, a value close to 1 is like a 70-year-old, an 80-year-old, very high of age. They actually do get up to like 1.2. I think it's like a 100-year-old. That's a very old person. And then here's the change. Okay, so now we have our percent values. So remember, our model will produce percent values as well. Here are our 32 values of male and female. So we can see that the first image in the batch is a woman, then a man, then a woman, then a woman, then a woman, then a man. And we're going to be using softmax loss to compare. Awesome. So here are our ethnicities. We can see that this is a Black individual. And then we have I think that is an Indian individual. And these are what we're going to be comparing our ethnicity scores against. Okay. Great. So what we want to do now is we want to actually put an image through our model like we've done before. So our model, this is our age pred, so prediction. We're gonna have a gender prediction as well. And we have an ethnicity prediction equals to model, and we're inputting our images. So all 32 of our images. Okay, so let's just take the time. I want to compare. Let's look at gender. The gender of the prediction and the gender of the ground truth. And let's, instead of looking at the entire batch, let's just look at the first 5. Okay, so 0 to 5, that's how you can do that. 0:5, that just says, give me the first 5 rows. We'll run that. Ages scores. Ages scores, where is that? Okay, that is in our model. I made an error. It's supposed to be age score. Age score. There's typo number 1. Okay. Perfect. So this is our first 5 in our batch. Our model is predicting, this is our prediction. Underneath. 45% chance it thinks it is a man, and it's a 57.4% chance it's a woman. It's basically just guessing. It's pulling a number out of absolutely thin air. Once we get training, we're going to see that number is supposed to get closer and closer to 100% female and 0% man. Okay, so that's what we're doing. So how do we measure how wrong we are? We do losses. But now we have a bunch of different losses. So we're going to have an age loss equals to, that is mean squared error loss. So I have the losses ready for you, just so they're ready to go. They're easy to use. And what we pass into it is we pass in our prediction. So here's our age prediction. And here is our age ground truth. Okay, so we're using MSE for that. Here's our gender loss. And instead of MSE, we're going to be using softmax loss because it's a classification problem. So it takes those percentages. Gen prediction. So that's the gender prediction. Takes the gender ground truth. And we got one more to do, ethnicity. Ethnicity loss is equal to softmax loss of ethnicity paren and ethnicity ground truth. Exact same thing. Okay. Now we're going to create total loss. Remember, it's just all of these added together. So our loss, the one that we are most worried about, here it is right here, total loss. Bam, bam, bam. Okay. Now, I want to be able to measure how much loss there is over each epoch. So we do that very, very simply. We just take total training loss. We just plus equal, that's the total loss right there, dot item. And then we're going to do that for each one of these. So we're going to have different categories for each one of them. I'm going to get through these really quickly. They're not too interesting. This is mostly just bookkeeping. Plus equal age loss, gender loss, ethnicity loss, dot item. Okay, that'll just add the numbers together. So over each batch, there'll be like, let's say there's 1,000 batches. It'll add all of those 1,000 together. At the very end, we'll divide it by 1,000 so we get the average. We've done that before. Okay. Awesome. So now we actually have to tell the model to train it, and we remember how to do that. At the very beginning, tell the optimizer, I'm going to feed you in some data. Get ready. Call zero grad. That's what Optim.zero grad does. At the very bottom, we are going to take the total loss and we're going to tell it to go backward. That tells the optimizer. It communicates to the optimizer. This is how much you need to change by. And the optimizer does that calculations, and it'll go in and it'll modify, it'll read how much it needs to change each one of those parameters. And then Optim.step, it takes a backward propagation step, is the official name, is putting that into data, saying, okay, I understand how much I need to change to make the model work better. Let's make that step. Awesome. So we have our loop ready. We now want to, after each epoch, we're going to do total training loss. We've done this before, more bookkeeping. This is our average calculations. So length of training data sets. So it's how many times we've been over the data set. We basically just, we do that for every single one. Total age loss, total gender loss, and we're just finding the average for each one of these within the epoch. Let's print it out. So what we're gonna do is a nice little tip in Python is if you're writing a string and you want to put values within a string. In other languages, I know in like Java, you have to do like hello plus 3 plus hi, and that'll print out hello 3 hi. In Python, if you want, you can take a string. If you put an F in front of it, so it's not inside the quotation marks, it's right on the outside, right here. It's called format, and it lets you do something with it. I'll show you what it does. So we can do epoch. We're going to put in epoch number. And that's what it does. If you put these curly brackets, it'll say whatever you put inside curly brackets is a variable. And I'm just going to convert this variable to a string, and it'll print out all nice. Okay. So loss. The first loss we want to print out, total training loss. Awesome. Then we're going to print out age loss. Not the most fun, but off we go. We're just going to do that for every single type of loss. So I'm going to just copy and paste it and change the variable names as I see fit. Okay. So we have our age loss. We have our gender loss. We have our ethnicity loss, and those are called age loss, gender loss, ethnicity loss. Now, if I've done everything correct, which I'm hoping I did, it should run. The one thing I want to do on top of that is I want to make sure we're saving, and I want to save every 5 epochs. So before we would run the entire model, and then we would save at the end. We're going to save every 5 epochs. So let's say it crashes on epoch 7, we can go back to our 5th epoch, and it'll run from there. So we're going to write if epoch. This is our modulus function. I'm sure you used it before, equals 0. So that's basically saying every 5 epochs. Actually, should be epoch number. We're going to save torch dot save. Remember, we've done this before. Model.state dict. Not state dict. State dict. State dictionary is what it is. It is a function. Looks like this, and then we're going to call it model.state. Okay. Now here it is. Let's make sure it runs. Hopefully everything runs properly. No errors. We're not getting them right now. When I ran this, we were working with big data. It is not necessarily the easiest. There's a lot of parameters we're dealing with now. Before we worked, remember day 1, we worked with 2 parameters. Now we're working with thousands, tens of thousands, probably hundreds of thousands, honestly. We're working with a lot, okay? So it takes longer. We're working with larger images. Before we worked with 28 by 28. Now we're working with 48 by 48, and that is going to reflect in the training time. We're training it on a CPU, so it's not anything too fancy. Most of the time in real big deal scenarios, you'll be training it on like massive GPU grids. Like Google has massive GPU grids where they'll be able to train this in a second, but we're going to take some time. So in my calculations, we're going to get up to 5 epochs. That's what we want to do. It should take about 15-ish minutes. So in that time, I want to show you some websites. I've wanted to show you some websites for a while that are very useful. The 2 I'm talking about are pytorch.org and something called Kaggle. Okay, and these are great tools for deep learning scientists of any level, beginners to pros. So PyTorch, this is your documentation website. Ooh, it's taking some time to load. This is where your documentation is. This is where your a lot of tutorials are for every single thing in PyTorch. This is PyTorch's official website. It'll teach you how to install PyTorch. So we're doing it on Google Colab. Oh, we ran into an error. Training data set is not defined. So it got through 1 epoch and then it messed up. It's called train data set. So there is our first error. My bad, guys. Let's run it one more time. Sorry about that. Okay, getting back to it. This is really where I started getting into deep learning pretty seriously. They have a lot of great information. They have great tutorials. I want to get into them. They have discussion boards, which if we click on that, they have Slack groups. I haven't really checked out the Slack groups. I'm sure they're great. But the discussion forums are great. They work much like Stack Overflow. You can ask questions on them. How to deal with dropout in between LSTM layers when using pack sequence, maybe a little bit out of your comfort zone, but you'll get there. You'll get there. There's compatibility issues. It's just like a way for people to discuss and ask questions. There's a bunch of stuff on this website. The one I want to get to is tutorials. Okay. Unfortunately, I have not had the time to give you guys a 100% bottom to top PyTorch tutorial. But if you want to take the time and if you're really serious, and I would recommend this to anything because you can use PyTorch. It's a beautiful tool. If you go over here, you check out the PyTorch tutorials, learn the basics. You can step through these and it'll teach you everything. So look, they're teaching about neural networks here. Object detection, that's very complicated. That is a masked recurrent neural network. That is a pretty complicated tutorial. But it'll teach you everything. It'll get you up there. I totally recommend checking it out. The big thing I want you guys to check out as well is that I use most frequently is PyTorch documentation. So if you ever want to know about how to implement a convolutional neural network layer and you don't really understand everything to it, you can't just come up in your brain. This is the website you go to check it out. You don't have to go to Stack Overflow as much because everything is really here. So here we are. We've used this before. Oops. Conv2D. Okay, let's make sure this is training. There we go. We got one epoch. Here are our losses. Let's see if they get better. So torch conv.2d. Let's check it out. This will give you all the information you need. Here are all the parameters in our neural network. We have in channels, we have out channels. Remember, those are the questions. It applies a 2D convolution over an input signal composed of several input planes. It's a little bit technical, can get a little bit confusing, but this is really where it's going to teach you everything. They have great notes. These notes are here to help you out. They'll give you examples. So here we are. So this is an input of 16 channels, output of 33. They're playing with stride and padding. We're not going to worry about that right now. But they have it about everything. They have it about different convolutional layers. They have it about, it's kind of a fun one. Here are optimizers. Okay, so remember how I told you the optimizers are really complicated? PyTorch agrees. Their documentation is essentially looking a lot like this, but it'll teach you there. All the information is there. If you want to check out the math, it's there for you to check out. Yeah, so pytorch.org, great website. It is really an all-star website. The next one I want you guys to check out, and this one is even more beginner friendly, I would say, is Kaggle. So Kaggle is, they do two things, and they do two things very, very well. They have some coding aspects and discussion boards, and they have some courses. In my opinion, they aren't that great. The two things that they do brilliantly is they have homes for competitions right here and data sets. And data sets. So if you want to create a project, if you want to learn how to do something, they'll create you, people post a bunch of different interesting data sets with like a bunch of users. So Taylor Swift, Spotify data. If you want to learn to, or if you want to create a model, use this data to create a model to do some sort of deep learning with Taylor Swift metadata, go ahead. It gives you all the information. This is what they're posting about everything. They'll post name of the song, name of the album, name of the artist involved, speechliness, loudness, liveliness. I don't know what that actually means, but they give you all the information and you can download them. So here is an Excel spreadsheet with everything about it. So if you wanted to run a machine learning task, you can do it about anything. And in fact, if you go over here, if you go to computer vision problems, like that, fish data sets, X-ray data set, very great, interesting ones, ASL data set. So that's pictures of hands for American Sign Language. If you want to learn how to translate, that is a great. And then, oh, wow, look over here. Age, gender, and ethnicity face data set. It should look quite familiar because this is where I get a lot of the data sets. I hope you guys aren't too surprised that I, okay, awesome. Now we're at 3 losses. So we can see our losses are going down as well, which is brilliant. And they're going down in gender, they're going down in ethnicity, and they're going down in loss. So we're on a good site. But I'm not going around taking pictures of a bunch of babies, okay? They've been doing that for me. I'm just grabbing them. Great website. So the other thing that they do very well is the competitions. So what they'll have is some person and Kaggle as well, Kaggle as a whole. They'll create, now these ones are pretty intense. Maybe not these ones, but for example, the NFL Big Data Bowl, they're creating a competition with $100,000 in prizes, doing something with the NFL. I don't know exactly what they're looking for. To learn about special teams before they ever play, before they play, never before. They're basically, the NFL is giving you a bunch of statistics and they want you to do some diagnostic stuff for them, and they'll give you prizes. So first place, $15,000. If you create the best model, $15,000. It's really fun. I've done a couple of these. There are some really, really smart people who crush them. But those ones are a little scary. The other ones, there's like the for fun ones, and then there's like the for legit ones. So here's some new to Kaggle stuff. So here's one that you guys might be a little bit familiar with. Here is everything for the MNIST data set. So the MNIST is, you should be able to recognize these handwritten letters, because I also stole the handwritten stuff from Kaggle.com. What this is it wants you to use computer vision skills. So we use simple neural networks. I'm actually going to challenge you guys. I would love to see it. If you guys email me or anything, if you guys actually end up doing this, I would love to see you guys do this challenge and try with convolutional neural network. See how much better you can perform. Give it a go. If you have any questions, please feel free to email me. If you need any help, I'd be totally down to sit down in a Zoom call with you. But I'd love for you guys to try to extend your knowledge. If you really want to learn about coding and how to create deep neural networks, this would be a great way to do it, because I know right now, because it's Zoom and it's online, I designed this course to be a little bit more interactive, a little bit more people coding for themselves and creating solutions right now. But because it's been on Zoom, it's been mostly follow along with me. If you really want to get coding by yourself, please, I recommend you guys check these out. These are really brilliant. They'll step you along the way. Okay, we are almost done, which is nice. Our losses are going down. Oh, chats. We have something in the chats. Great workshop, thanks. Yeah, no worries. See you next time. If you're a little bit longer, don't worry. I just want to train 5. If you guys got to leave, it's okay. I'll put some spoilers. I have run this before. If it trains after 5 epochs and you run it in it, it'll produce some pretty okay results. Okay, so did that. I'm going to just give it some time to make sure it's saved. Okay, awesome. Now we can hold that. Okay, it's trained for 5 epochs. Now, like what we did before, we're going to call, we're going to load into the model. Okay, so I'll do this really fast. Model.load underscore load state dict torch.load. And then the load name that we're going to do is, oops, don't want that. I actually pressed a button that made my code run. Did not want that. It's going to be called model.state. Yeah. Okay. See you, Dawson. Have a good one. Model.state. If you stay to the end, we're not going to train. We've already trained. We're taking our train data and we're going to test it. And this is going to be real quick. So let's just call test. The tests I've done for you. We're going to pass in our model, and we're going to pass in our test data set, obviously. Test underscore DS. Okay, we're going to run that, and we're going to see what happens. Take some time. Awesome. Okay, so what it did is if you're looking at the numbers like this, I'll also show you guys the visual component. Here are our losses. Those are our testing losses, just to make sure that they're not too far off from our train losses. We got 75% of the ages correct within 10 years. We did a great job. Gender, we got a 93% of the time correct. And then ethnicity, we got an 88% of the time correct. So our model's performing well. I want to show you guys what it looks like with the actual images. It's a lot more easy to see. So I am going to show you. If we do that, run, blah, blah, blah. As well, awesome. So P at the top, that's predicted. And T is our target or our ground truth. You can see truth of target. So you can see this picture. They identified it as a 17-year-old African-American woman, Hispanic woman. And they got everything right. The age was 10 years off. She's actually 27, but not too bad. Could be worse. And you can look at around. They do a pretty good job. They're here. Say hi to John Krasinski. Here he is. They're not too bad. So you can see a lot of correctness. They do get it wrong. They get it wrong a lot more than we did with the MNIST data set. We also did only train it for 5 epochs. So I have also done us the favor of training it for you. I trained it for 50. So if you do sort of model.state, if you grab it from my GitHub, week 4 / model.state, that is my pre-train. I trained that for 50 different epochs, and you should see it's a lot better. So this actually, the amazing thing is that this model, I'm fairly certain, I haven't actually done the survey, but this is doing a better job at predicting age than I think I could do as a human being. Like, it is uncannily close. They predicted this as a 69-year-old woman. She's actually 68. Now, this woman is 23. They predicted her as 38. But looking at this image, just this pixelate data, I would have no idea. That is definitely a tough one. Age is definitely still the hardest component. Let's, if we go up to test again, if we comment this out, ignore the break because it'll only show the top batch. If we do that, we'll see actually how good, if we train it for long enough. We definitely didn't train it long enough, like those 5 epochs. If we did it for 50, which is what I did, our correctness, it gets age correct 90% of the time, gender 97% of the time, and ethnicity 95% of the time. So we actually did an outstanding job. It's a tough issue, but the convolutional neural networks are a powerful tool, and they can create really great performance gains. Other than that, that's it. Next week, convolution part 2, we're diving into the parameters. Next week, we're also going to be working on a brand new type of problem. So not classifying. We're going to be working about image detection. So it's going to be picking out like, where is a hand or where is this? Can't spoil it for you guys. That's what we're working on. Once again, as always, thank you so much for showing up. You guys are doing great. I love my team showing up. I see the same names every time. I'm so excited for you guys to get your diplomas. Thank you for coming down. If you have any questions, you can email me. And like I said before, if you guys want to really get some hands-on coding, I would recommend checking out something on Kaggle, one of the easy competitions. I think it'd be a great progress for you guys. And if you do it, let me know, okay? I'll see you guys soon. Next week. Enjoy your week. Enjoy your weekend. Have a great one. See you guys.